video is an introduction about black holes. Black holes are one of the most mysterious things in our universe. They have occupied the minds of the most brilliant scientists in the history, most famously Stephen Hawking. Black holes were predicted a long time back using Einstein's general theory of relativity. Since then, there has been a lot of research about black holes, but even today, a lot of things remain unknown about black holes. So let us try to understand black hole in the simplest way possible. Let's start by discussing the history of black holes. Albert Einstein is the name that pops up in our brain when we think about black holes, but black holes were predicted a long time before Einstein's theory of general relativity. The idea of a body so massive that even light could not escape was briefly proposed by English astronomer, pioneer and clergyman John Michell in a letter published in November 1784. He referred to these bodies as dark stars. But the golden age for the black holes actually started only after the publication of the general theory of relativity in 1915. Soon after this, Carl Schwarzschild calculated the equation for a Schwarzschild black hole, which is a non-rotating black hole. We have many other types to talk about, so just hold on for now. We will talk more about the characteristics of these black holes in the next section. After this discovery, black holes have occupied the minds of a whole lot of physicists and have been the most extensively researched and studied topic by scientists, of course only until the discovery of quantum mechanics. Now let's talk about the basic structure and properties of a black hole. The most amazing thing about black holes is that they do not have many properties. What I mean is that if you want to distinguish between two people, there are too many features including physical and emotional behaviors which differentiate two people. Or you can differentiate two objects by their color, looks, and material they are made up of. But black holes are completely dark and black. The only three features that every black hole demonstrates are mass, angular momentum, and charge. This is also known as the no-hair theorem. It postulates that once a black hole achieves a stable condition after formation, it has only three independent physical properties: mass, electric charge, and angular momentum. The black hole is otherwise featureless. If the conjecture is true, any two black holes that share the same values of these properties or parameters are indistinguishable from one another. The degree to which the conjecture is true for real black holes under the law of modern physics is currently an unsolved problem. Based on the rotation and charge, there are four types of black holes. The simplest static black holes have mass but neither electric charge nor angular momentum. These black holes are often referred as Schwarzschild black holes, after Carl Schwarzschild, who discovered this solution in 1916. The other two types include non-rotating charged black holes and rotating but uncharged black holes. The fourth type of black hole is both rotating and charged. This is often known as Kerr-Newman black hole. The two defining features of a black hole are its event horizon and singularity. As we know, the gravitational pull of a black hole is the strongest in the universe. The event horizon is the boundary in space near a black hole from where the effect of its gravitational pull is so large that nothing can escape it, including light. The event horizon is referred to as such because if an event occurs within the boundary, information from that event cannot reach an outside observer, making it impossible to determine whether such an event even occurred. As predicted by general relativity, the presence of a mass deforms spacetime in such a way that the paths taken by particle bend towards the mass. At the event horizon of a black hole, this deformation of space becomes so strong that there are no paths that lead away from the black hole. If anything passes the event horizon, it is stretched along its length and compressed along the width. Of course, because of the gravitational pull. This process is so extreme that physicists have actually named it spaghettification. Now, talking about singularities, they are points in space-time where physics laws go crazy and yield infinity as the only answer. At the core of the black holes lie a singularity as predicted by the general theory of relativity, because in this region the curve of space-time becomes infinite due to extreme gravity. Anything that passes the event horizon of a static black hole, there is no way it can avoid crashing into the singularity. But the story changes if it is a rotating or a charged black hole. A whole new theory of wormholes and parallel universe arises here, which are not only science fiction but theoretically proven. We will talk more about these in the upcoming videos. Now that we have the basic information about black holes and we also know how they are formed by the collapse of stars and other high energy collisions, as I've discussed in my previous video. Now let us see how do we observe a black hole if they emit no information like light or any kind of signals. By nature, black holes do not themselves emit any electromagnetic radiation other than the hypothetical Hawking radiation. So, astrophysicists searching for black holes must generally rely on indirect observations. For example, a black hole's existence can sometimes be inferred by observing its gravitational influence upon its surroundings. Astronomers can also observe the motion of stars around any unusual object and play with equations to figure out if the object at the center is a black hole. The proper motions of stars near the center of our Milky Way provide strong observational evidence that these stars are orbiting a supermassive black hole. Scientists can also observe the gravitational waves to detect black holes. In 2015, the LIGO Gravitational Wave Observatory made the first ever successful direct observation of gravitational waves. The signal was consistent with theoretical predictions for the gravitational waves produced by the merger of two black holes, one with about 36 solar masses and the other around 29 solar masses. This observation provides the most concrete evidence for the existence of black holes to date. The first image of a black hole was also developed in 2019 using false color, which shows the light bending around a black hole with the center completely dark. There are few other interesting ways of observing black holes, including the observation of X-rays and observing binary star systems. Another proposed way includes gravitational lensing. It is a process where the light coming from behind is bent by massive objects containing a lot of mass, as predicted by the general theory of relativity. The deformation of space-time around a massive object causes light rays to be deflected as much as light passing through an optic lens. Observing this strange phenomenon helps in locating the presence of black holes. Even after knowing how to detect black holes and their features and characteristics, there is a lot not yet understood about black holes, including black hole thermodynamics, Hawking radiations, Penrose diagrams, and much more. I'll try to introduce these topics to you in the upcoming videos, so stay tuned. This was all about the basics of a black hole, its characteristics, and its structure. Thank you for watching, and I hope you liked it and it was informative. Make sure to check out these videos for more of such content.